So problem number one. A kinetic sculpture rests on three adjustable supports of positive lengths x, y, and z. For the sculpture to remain balanced, the supports must satisfy 2x plus y plus z equals 4. The sculpture stability score is given by x squared yz. Find the greatest possible value of the stability score. So, does anyone have an idea how to does anybody know, have an idea of what methods to try? Does anyone still have any ideas? Okay, I'll wait for derivatives. Yes, that could work. That could work, but there is a non-calculus solution to this problem that we can use. But derivatives are also a solution. Actually, um, I'll wait for like a minute for anyone else to give ideas. But you can message here in the chat. But for now, I'll just um write a general. I'll write up a like um I'll make a write up of the derivative solution. So here's the first solution. Okay. So notice that since we know that actually it's 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 not the solution I have in mind about derivatives uses Lagrange multipliers. Now this is overkill, like overkill, but I think it's not a nice method to first introduce people to, because normally with derivatives there for this problem there are three variables. So that means even if you isolate one of the variables, like for example y is equal to 12 minus 2x minus c, then you a still get an equation with two variables. So oh yeah, someone in the chat said EMGF. That is the solution. We'll get into that later. So for this solution, for Lagrange multipliers, actually wait no. I'll touch on that later. Actually, I'm not gonna do Lagrange multipliers then. I think it's more important to actually give the solution. So we're going with AMGM first, right? Here's the idea basically. Um, for AMGM in AMGM, the AMGM the arithmetic mean geometric mean theorem. I mean, no, sorry, the arithmetic mean geometric mean inequality says that for positive real numbers, a1, a2, etc. up to an, their arithmetic mean, which is basically the sum of all the terms divided by the number of terms, etc. plus a sub n all over n is greater than or equal to their geometric mean, which is basically the nth root of their product. So a1 times a2 times all the way up to an, a sub n. So how can we use this theorem in our problem here? Because here's the question. If we just use AFGM directly on 2x plus y plus z, we get 2x plus y plus z, right? 2x plus y plus z over 3 greater than or equal to the cube root of their product, which is 2xyz, right? But thing is here, this is not x squared yz. The 2 is here. It's not on the exponent. So this, we can't use LMGM here directly to find our to find the solution. So what does any of you suggest we do? Yes, Andrew. Um, we split the x into we split the 2x into x plus x. Why? So that we can treat those x terms as separate in our um arithmetic mean, so that our geometric mean yields x squared instead of x, because now there are two x's instead of one 2x. It's a bit confusing to say, but you get what I mean, when I write it out. So instead of three terms, there are four terms, and this instead is greater than or equal to fourth root of x times x, which is x squared, and then you multiply by y and z. Now notice by splitting the terms of x and x, you've effectively increased the exponent by one. And in fact, this is a very useful strategy for dealing with weird powers and with different powers from what would usually be in AMGM. But it is a very useful technique in many inequality problems. So here we know that since 2x plus y plus z is equal to 12, this must be 12 over 4 or 3. So 3 is greater than or equal to the fourth root of x squared yz. And so 81 is greater than or equal to x squared yz. Or on other words, x squared yz is, sorry, x squared yz is less than or equal to 81. Now, are we done yet? That's the question. Because we have x squared yz is less than or equal to 81. But are we done yet? We have a upper bound for x squared yz. But again, um, we may or may not be done with this question. So Does any of you have any ideas on how to proceed from here? Yes, I like it. That's exactly correct. Oh, sorry. So, um, we're not done yet because we don't know if there are actual values of x, if the upper bound 81 can actually even be achieved. So we need to check for values of x, y, and z that satisfy it. And notice, EMGM has equality case when A1 is equal to A2 is equal to A3, sorry, equal to A3, equal to A4, etc., etc., right? So we need to check for this equality case. And if it holds true and this satisfies our equation, then we are done with the problem. So if we set x is equal to y is equal to z, then we know that x is equal to 3. Then we know that all of them are equal to 3, right? Well, this satisfies the first equation, which is um 2 times 3 plus 3 plus 3, which is 12. And also, this is the equality case for our inequality because x squared, I'm no 3 squared times 3 is equal to 3 to the 4th, which is 81. So, thus, this is our equality case, which works. And since we know 81 can be achieved, um, we know that 81 is our maximum value. So therefore, it must be the answer to this question. Speaking of questions, does anyone have any questions? Oh yeah, forgot the Lagrange multipliers. Um, it might be a little complex, and I might actually refer to a handout here. But basically, um, for Lagrange multipliers, we take partial derivatives. So, for, oh wait, wait, I'm going to refer to a handout for Lagrange multipliers because it's a very it's kind of an advanced technique. So, if you're okay with so basically here, the method of Lagrange multipliers is that yes, this looks scary, but basically the essential concept of Lagrange multipliers is that we take partial derivatives um with respect to x, y, and z, or basically all the variables here. So in here, we first take the partial derivative of this, which is with respect to x, which in this case is 2. Yeah. Um. So we should first note that our f of x is the um it's a maximum value we want to find, which means that it must be x squared y z, right? And our g of x must be equal to 2x plus y plus c, right? So essentially, we take the partial derivative of 2x plus y plus c and x squared, which we take the partial derivative of g of x, right, with respect to x, y, and z, which means we have a, and then we multiply it by our Lagrange multiplier, which in this case will be lambda, I'm pretty sure. So 2 lambda, right? And then we take, and then we take the partial derivative with respect to x as well, which in this case must be, if I'm not wrong, 2xyz. And then we do this for all the other variables. So with respect to y, we have lambda is equal to, then we take this with respect to y, which is x squared d. And then we have we take it with respect to z, which means we have x squared y, right? And then all we have to do is solve this system of equations, and then that system of equations is the yields the maximum the an extreme value, which in this case must be the maximum value, because the minimum value, yeah. In this case, it's the maximum value. Actually, wait, yeah, because we can set one. If the minimum value, we know the minimum value must um be infinitesimally close to 0, 1. Yeah, just can just set y and be really close to 0 as some as like 6 near 6. But either way, first we must solve the system of equations, and then after solving the system of equations, we must verify if it is a maximum or a minimum. If it is our maximum, then we're done. So in this case, um solve the system of equations. We Okay, actually, wait. Does any of you have any ideas how to solve the system of equations to get the values of x, y, and z? Just a small question first. I know we're getting a bit off topic from the sample problems here, but um, I think this is very interesting to talk about. And after that, I'll quickly talk about the other problems. Okay, in that case, um, we can divide the second equation by the, no, we can divide the second equation by the first to get the x over y over 2y is equal to 1 over 2, right? And so we get x is equal to y. And we can repeat this for x is equal to z as well, because y and z is symmetrical. So we notice that x is equal to y is equal to z, right? And this is basically our the um same thing we did in the AMGM solution, but it's a lot faster, I'd argue, if you know how to take derivatives fast. So this is a very useful concept, especially in more advanced inequalities.